Hi, my name is Rohan Aluri, and this is my Physics 2211 Constant Velocity Lab. Some of the intended goals of this lab were to analyze the various positions of an object moving under constant velocity through the use of the tracker software in order to create an experimental model of the object's motion, to create a computational model that resembles an object moving under constant velocity through Newton's second law and the GlowScript software, and to observe both of these graphs and explain the key differences and why we are interested in the lab's implications. Some of the physics concepts that were involved in this lab include the average velocity formula, and assuming that we have constant velocity, that the initial velocity and final velocity are equal to the same value, Newton's second law, and then assuming that the net force is equal to 0, that once again final velocity and initial velocity are the same, and the kinematic equation to find change in position. We should be interested in these physics concepts because the relationship between net force, velocity, and position can be manipulated to change the movement patterns of any object. On the left, you can see Tracker that spotted all the individual points that is used to track the movement of my water bottle. On the top right, you can see a position time graph that has a linear and decreasing slope. And at the bottom right, you can see all the individual points of the times and the x-coordinate of the water bottle rolling across the surface. On the right-hand side, you can see another graph that displays the position along the x-axis on the y-axis in terms of meters and the time in terms of seconds on the x-axis. Overall, you can see a fairly linear and a decreasing slope. On the left, this is my computational data code via GlowScript. Some of the values that were changed were the initial position and velocity vectors, the time, and as well as the last print statement that says that we were going to print the time and the position of the ball in terms of x-coordinates as well. On the right, you can see a fairly linear and decreasing slope once again. In order to calculate the average velocity that was used in the computational data calculations in GlowScript, we had to take some of the values from Tracker, such as the initial and the following frames. Getting the value of the time and the x-coordinate for the water bottle in the initial and following frame we can calculate the total velocity for this water bottle in the initial movements, which calculates to be negative 0.229 meters per second, and this value was inputted in the GlowScript code. When graphing both the theoretical and experimental lines in the same graph, we can see that the average velocity for the experimental line was negative 0.192 meters per second, and the average velocity for the theoretical was negative 0.229 meters per second. We can tell by the position time graphs that experimental line has higher values when compared to the theoretical, and that velocity is constant when taking the derivative of this graph, assuming perfect conditions. We can also tell that both the theoretical and experimental start off and end with potentially the same velocity as can be seen by the overlap. In the middle, however, the experimental data shows a slight acceleration as they can be seen with higher values. This may occur due to potential sources of error such as a surface being slanted, friction on the surface, my hand adding force to the object, and the point of mass being inaccurately identified. If we were to change the positive x and negative x values, then I believe that the object would be traveling in the opposite direction. In this case, however, my results would change as the velocity would go from negative to positive and the object would travel to the right instead of the left. However, some results would remain the same, such as the magnitude of the velocity and the force are not being affected and they do not change. Additionally, theoretically, I believe that it would be difficult to identify all the different forces, push or pulls, that act on an object, as air resistance, the force of friction, and the force of gravity due to a slight slant in the table should all be accounted for as the experiment was not conducted in a closed system. However, we can conclude that the sum of these forces is equal to 0 as, for instance, the additional force of my hand and gravity would be equal to the force of friction that yields a net force of 0. After completing the lab, I believe that I received further insight regarding the underlying relationships between the physics concepts of position and velocity, as well as velocity and net force. This can be seen through comparing the experimental and computational models of my object. The difference between the slopes of the graphs at varying times displayed how there was potential sources of error within the experiment. If we were to replicate this experiment in a closed system, accounting for negligible friction in an object that is perfectly cylindrical, then the object would undergo constant velocity. Through the implications of this experiment, additional questions begin to arise as to how would the computational and experimental graphs change if the object used was non-cylindrical, and to what extent does having no net force on an object mean in a perfect world with no friction.